Welcome back to Structural Dynamic lecture. Myself, Dr. P. Naresh. Today we are going to discuss regarding lumped mass system as well as continuous system. Okay, we have different type of systems. When we analyze a structure by using dynamic forces, we have to divide the mass into different parts. There are two methods are available to divide those mass. One is continuous system. Either we can consider total mass of the body continuously, otherwise we can discretize the mass at different distances, okay, different locations. Okay, those are the two methods we have. One of them is continuous system. Okay, what is the continuous system? Continuous system means where the mass is distributed continuously. The mass will be distributed continuously over the structure. Okay, and this continuous system mass is distributed continuously throughout the structure, throughout the height of the structure. Okay, throughout the structure in any direction, and if you means in direction where you are going to analyze. Okay, the continuous system is this mass is continuous throughout the structure, throughout the height of the structure. Okay, total height will be considered as the continuous system of mass. Okay, like some of the example you can see a special type of structures like cooling towers, they we used to assume as continuous systems. Bunkers, silos are considered as a continuous systems where mass is distributed continuously. Okay, mass will be distributed continuously. For suppose if you see in buildings, mass won't be uh, distributed continuously. We can say at every floor level there will be a type of mass will be given. Means every floor slab we used to consider as a one type of mass. Okay, for suppose for slab 1 this is having lot of mass, large mass. Slab 2 it is also have some mass. Slab 3 floor level 3 it is also having some mass. Okay, this one is the lumped mass. We can see different type of discretizations in the mass, but in continuous system it won't have any story any height of the mass. Throughout the height mass will be same, means continuously varies. We can see uniformly distributed over the structure. Okay, you can see the loads which are applied UDL, uniformly distributed. Uniformly distributed loads will be applied throughout the length. Okay, like that mass also distributed throughout the length. Okay, those type of systems we used to call as the continuous systems. Okay, some of the continuous systems may have different type of profiles. Their profile loading profiles will be there. They we used to assume as like rectangular type of profile, trapezoidal profiles, or hyperbolic hyperboloid. Each are the different type of profiles of the that particular structure after applying load. Okay, means deflected shapes we can say. And the response due to dynamic loading varies for different profiles. These responses means here a response is nothing but we have 3D response parameters. First one is displacement, second one is velocity, which is the rate of change of displacement, and third one is the acceleration, which is nothing but rate of change of velocity. Okay, these three parameters. The, the response due to dynamic loading varies for different profiles. These responses, these deflected shapes will be varies for different type of shapes, different type of profiles. Okay, means different type of dynamic loadings, these will be varies. Okay, this is regarding the continuous system. Actually, we have different type of structures. We used to analyze structures like this. Simple structures, as we know, structures simple because they can be analyzed as a concentrated or lumped mass M, the mass M supported by a massless structure with stiffness K in the lateral direction. Okay. When, if you see here in this diagram, they assume this structure, they have taken total mass of this beam and this mass, mass as the lumped mass. Okay, and this mass is the mass of this beam is we used to take as lumped mass, as a single mass, or different two types of masses or three types. We can discretize this mass. Okay, this the total weight of this structure we used to take as a single mass m or number of masses. Okay, and we assume this one is the massless structure is resisting this total mass. One massless, we used to assume a massless structure is resisting this total weight, total mass of the body. Okay, when we apply the external force, this mass will be moves in the direction of the force. Okay, and this particular mass is supported by a massless structure, and that massless structure having the stiffness K. The stiffness of that massless structure is K, we used to assume in the lateral direction. Okay. Okay, this one is called as the simple structure. When here we are not dividing this mass into different parts, we use here we are assuming total weight of the body, total mass of the body, a single mass, lumped mass system. Okay, this one is we used to take as a simple structure. In case of lumped mass, the lumped procedure is a large proportion of the total mass actually is concentrated at a few discrete points. This mass, this total mass will be discretized in different parts depending on requirements and depending on deflected shape of the this beam or structure or deflected shape profile of the this particular structure. Okay, here we used to discretize this particular structure in different parts, and we used to assume some discretization points, means the junction of two points, two parts we used to take as a discretized points. Okay, then the mass of the structure which supports these concentrations can be included in the lumps, allowing the structure itself to be considered weightless. Okay, and what they are telling here, the mass of the structure which supports these concentrations can be included in the lump. Okay, the parts of the loads which we have divided, those masses we used to consider as lumps, and allowing the structure itself to be considered as a weightless. And moreover, we used to assume this structure as weightless. Okay, we used to consider this weightless structure is carrying the mass m, lumped mass. That mass is used to call as the lumped mass, and that mass is discretized in different parts. If you take beam, this beam load has been this beam can be divided into different parts. If you see diagram like this, if you see diagram here, that beam has, here we are assuming deflected shape like this because of this external force. This total mass is moving in downward direction, it is forming a deflected shape like it is forming a profile like this. Okay, this is a profile of this particular mass system when we apply the external force. Okay, but the requirement of this particular profile, we can divide this beam into three parts. If you want to divide in more than three, you can also divide into more than three parts, but here I am going to divide this particular mass system into three parts. Okay, half of the 1/3 portion of the mass I am considering as mass m1, next one m2, and third part as m3, and these three parts are carrying masses m1, m2, m3. These three are the lumped masses. Okay, and this is the diagram of lump mass idealization of the simple beam. You can see this beam has been idealized as lump mass with masses m1, m2, m3. And because of external force, when we apply the sudden dynamic force over the beam, it will be moves downward direction, and it will causes and it leads to the inertial force. Okay, because of this external force, mass 1 moves in this direction and it causes the force inertial forces Fi1, whereas inertial force of mass 2 will be Fi2, inertial force of mass 3 will be Fi3. Okay, these are the inertial forces which moves with mass, which are having weight. Okay, the forces which are generated due to the mass of the body, those forces we used to call as the inertial forces. Here these are the forces. Okay, these are the inertial forces. These type of systems we used to call as a lumped mass idealization of a simple beam system. Okay, in this one we used to assume some of the parameters, that means some assumptions are required. This procedure is based on the assumption that the deflected shape of the structure can be expressed as the sum of a series of specified displacement patterns. Sum of specified displacement patterns. Okay, you can see for this particular displacement pattern we got three type of idealized lumped mass systems, and we have idealized this lumped mass like this. Okay, a simple example of this approach is the trigonometric series representation of the deflection of a simple beam. This deflected shape of the beam we can define or represent by using some trigonometric functions like sine or cos. Okay, if you take here displacement of the body, if you take boundary conditions for this particular simply supported beams, okay, by using simply supported case and boundary conditions, we can get the equation V of x. This is the maximum deflection. The body is deflected in the downward direction. The deflection is 0 at a distance of 0. At a distance x is equal to 0, deflection will be 0. At x is equal to, if body is having x is equal to not equal to 0, then we can get the equation like this. At 90 degrees, okay, we can get the 1. At some distance we can get x is equal to some distance, we can get L value. Okay, number of modes will be 1 only. Here we are assuming one mode shape. Okay, only one displacement we are assuming, one deflected shape. For the deflected shape we can get the displacement equation. Bn is a constant parameter, whereas sine into n5 x into x by L. Okay, and this one is the summation of number of masses, lumped mass systems you have considered. N is equal to 1 to infinity. If you take 3, then we used to take B1, B2, B3 like this. B1 sine of pi x by L, B2 sine 2 pi x by L plus B3 sine 3 pi x by L. This is the equation for 3 lumped mass system. Here we can see the infinity number of lumped mass systems. Depending on this diagram, these diagrams and summation of all the forces, we can get the displacements of the bodies. And the deflection shape may be expressed as sum of independent sine wave contributions as shown in the figure. Okay, sum of the independent. This one is for number of independent wave portion profiles of the beam. We can use this one. If you get more than one, then we used to go for the summation of independent sine wave contributions. Okay, and whereas A is nothing but A here, N is nothing but degree of freedom. Okay, degree of freedom depends on number of mass system. Every mass system will be having the one degree of freedom. If you apply the force in this direction, body will be try to move in downward direction. Here for every mass system we can get 1 degree of freedom, downward direction. Okay, n is the downward degree of freedom approximation would contains only n terms in the series. Okay, n will be depends on the number of masses you have applied here, lumped masses you have considered here, and here in this equation also n also we used to consider number of n masses they are generating lumped mass profiles. For example, and you can see the figure which has been given in the next slide, okay, for understanding of this particular equation. For suppose here I am going to take 3 mass system, and 3 mass systems will have 3 degree of freedom system. For each degree of freedom system, if you are going to assume single degree of freedom system, we used to consider one deflected shape like this for one mass. Okay, for one mass we can get the equation b1 displacement v of x is equal to b1 sin of phi x by L. Equation v of x is this one, this two only. There is no need to add other terms. Here we used to use first term for first displacement. Okay, if you want to find mode shape for two masses, two mass systems, we used to consider two masses, here one mass and here one mass, and these both the masses are moving in opposite direction, and these two can create maximum displacement, and then v of x will becomes v of x is equal to b1 sin 5x by L plus b2 sin 2 5x by L. This is the displacement for 2 degree of freedom system. If you want to find 3 degree of freedom systems, means 3 displacement systems, then equation will becomes v of x is equal to v3 sin 3 5x by L. Here we can see the 3 mass systems are having 3 different displacements. Okay, we can see here sinusoidal wave of the equation. We can see the sine waves, and this figure indicates sine series representation of simple beam in deflected shapes. Okay, this is regarding the lumped mass system. Okay, for lumped mass system we used to calculate displacements like this. If you are going to take n number of degree of freedom systems, we can use n number of degree of freedom system, and we can use this particular equation, and we used to summarize, means we have to take summation of all these displacement parameters. Okay. And regarding damping, okay, I am ending here itself. Okay, we will see remaining things in next videos. Okay. Thank you everyone. Signing off, Dr. B. Naresh.